Okay, in this video, let's look at the first example problem, a horizontal projectile. So we have a ball. So this goes back to our intro video. The ball that's kicked off the cliff has an initial speed, in this case, of 10 meters per second. The cliff is flat, so the initial speed is horizontal. The cliff is 53 meters off the ground below. How far from the initial X position does it land? So a couple things. How do I know it's a horizontal problem? Okay, if you ever are told it rolls off or you jump off with initial horizontal velocity of some certain or initial speed of, or a car drives off a cliff, hopefully not, but in practice example problems it can work, or if it says there's no initial vertical velocity, these are all cues from a problem to tell you that it's a horizontal problem, meaning it has some initial x velocity, in this case 10 meters per second, and my initial y velocity is 0. That's the key. That makes it simple for us. That makes it a horizontal problem. Alright, so how do we solve these? Well, the first thing to do is to separate my information now, my given table, into information pertaining to the x direction and information pertaining to the y. Because I know it accelerates in the y, but does not accelerate in the x. So the first thing I can write down, always, for a projectile, ax is 0, ay is negative 9.8 meters per second squared. Now we are neglecting the effects of drag for these problems. If we included drag, it would make it more complex. For these first set of problems, we are not counting drag. And actually, for all the problems we do, we won't count drag. Because really, to handle that effectively, we have to apply some calculus. Because the force of drag varies with speed. So we have a lot of things going on. Okay, x acceleration 0, y acceleration negative 9.8. All right, I also know my initial velocity in the x is 10 meters per second. My initial velocity in the y is 0. And this is a condition of a horizontal problem. All right, well, what else do I know? Well, I'm given the height of the cliff is 53 meters. So the way I'm going to set these up is I'm going to consider my ground, my y position of 0. And so anything that's starting above the ground and headed towards the ground, I'm going to have as a negative displacement. 53 meters, and again, that's a y. Make sure, the most mistakes are made in these problems mixing x and y dimensions, so make sure you keep those squared away and straight. Okay, what else do I know? I think that's it. Okay, what I do know though is that these two directions will be linked by time, because whether I look at the problem from the perspective of how it moves in the x direction until it hits the ground, or I look at the problem from how it moves in the y direction until it hits the ground, the time will be the same, right? The time is independent of the direction I'm looking at. So what will happen? Well, what's going to happen is my ball is going to slowly accelerate till it hits the ground, and it's going to eventually land, and it's going to land some delta x below my initial x position. Alright, so to approach this, I got to look at the y and the x information and figure out how do I eventually get delta x. That's my missing variable. So just like I showed you with the kinematics problems, these are kinematics problems. They're constant acceleration, constant velocity problems. So in the x direction, the only thing that matters is my change in x over the amount of time it was in the air. Because this is constant. There's nothing accelerating it in the x direction. So this is the only equation that will apply for the x direction. Now in the y direction, I have constant acceleration motion. So I'm going to use my constant acceleration equations. And notice I added in the y subs, the x subs, so we can keep those straight. Y delta t, but the delta t's are just delta t's, right? Because it doesn't matter whether I'm in the x or the y, delta t's are the same. So vy squared equals v initial y squared It's 2 times AY times delta Y. All right, well, what do I want to find? I want to find delta x. So what I need, so I'm going to simplify this for delta x. Okay, I have my initial velocity in the x, that's 10, but I don't have the time. So I need to, in order to find delta x, I need to find the time. So this is where we go back to our y information. Now let's solve the y. Let's just change the color. I should have done this a little bit earlier. So how do I find time with my delta y information? Well, let's look at my equations, right? If I want to find time, I can either use the first or the second equation. The first, I need the final velocity in the y, the initial, and a. Well, I don't have final velocity in the y, so I would need to find that first. So let's look at the second. Do I have delta y? Yes. Do I have v naught y? Yes, it's 0. I have ay? Yes. And actually, because this is 0, it becomes a simpler, more simple equation. So I can use equation number 2 to solve for time. And then once I have the time, I can plug it back to here. So projectiles are typically always two-step, minimum two-step problems. So delta y is v naught y delta t plus 1/2 ay delta t squared. Well, I know this is 0, so 0 times any time will always be 0. So delta y is 1/2 ay delta t squared. So I'm solving for delta t, so let's multiply both sides by 2 to get rid of the half. And then I'm going to divide by ay. So I get delta t squared is equal to 2 delta y over ay, and we'll have to square root that. So delta t is going to be my plus or minus square root of 2 times delta y, which is negative 53 meters, over a sub y, which is negative 9.8 meters per second squared. So the meters cancel, the seconds squareds go to the top, so I have square root of seconds squared, which will be seconds, which is good, which fits. So let's check my calc. Alright, when I plug that in, I should get a time of 3.289 seconds. And I know it's positive because I can't have a negative time. So once I know the time, I can put that back in my table. So that means the ball is in the air for 3.289 seconds, which means it falls for that long, which means it moves to the side at this initial velocity for that long. So I go back to, now, I should call this delta t. Got to be consistent. I'm sorry for that. So delta x is 10 meters per second times 3.289 seconds. Seconds canceled. I'm left with meters, which is good. So I get my delta x is 32.89 meters from the base of the cliff. Okay? So what were some of the keys there? To recap, I keep my x and y separate. Ay is negative 9.8, ax is 0. If it's a horizontal problem, initial y is velocity is 0. The x velocity is constant throughout. And I connect the two with the time. And there is example number 1.